Well, thank you very much for inviting me to give this talk. And I'm very impressed with what's going on here at USC. I wish we had some similar program at Stanford. I came to United States more than 65 years ago, and been spent most of my time in Northern California, teaching at Stanford. And over the years, I've been involved with collaboration with Armenian astronomers, especially during Soviet era, where Armenia was the center of astronomical research in the USSR, and still continuing that collaboration. And thank you, ASOF, which I'm a member, for organizing this. And so my talk is going to be something very different. All right, as the title suggests, I'm going to talk about gravitational lensing and the caveat about something which Einstein thought couldn't be done. So we'll see how that came about. This is a short outline. Before talking about gravitational lensing, I want to say a few words about our current view of the universe. And the main thing I want to emphasize is that as we learn more and more, we find the universe to be more strange and strange. I will try, hopefully, convey that to you. Then I'll talk about gravitational lensing and how important it is for studying the universe and the ways we are using it. And if there's time, I may even talk about the future of the universe. There are two ideas. One is that the universe will end up to be a cold and lonely place, but the other possibility that just came out recently since some observation may prove that to be the opposite of that. So, well, the main questions that probably a lot of people mind when we study the astronomical sources and universe is what is the origin of the universe and life, and how do life and the universe evolve? The evolution is governed by known forces, physics, chemistry, biology, and there's a lot of understanding of how things evolve in the universe. And there are lots of experiments, lots of observation proving these ideas. But origins is very difficult. Origin of life, my view, we could make some progress, eventually discover. We are discovering a lot of planets around all the other stars in the universe, essentially. And we are hoping to find places like the Earth where life could begin. Of course, life could be something different too. But I think still the laws of nature that govern that aspect we can understand. But the origin of the universe is, in my view, most likely unknowable. When I was a young man in Iran and at night sleeping outside, staring at the stars, I always wondered, we were told that God created everything 5,000 years ago. I always wondered, who created the God? So that was beginning of my search for origin of the universe, and it never ended. So there's an interesting story. When Darwin discovered the evolution of species on the Earth and showed that life has been going on a lot more than 5,000 years, maybe billions of years. There were people who said, well, there is no contradiction between that and what the Old Testament tells us about the universe. There was a philosopher named Bishop said when God created everything, it also created all the fossils in the earth. So the people looking at the fossil thought life could be very old. So this is not something that you can disprove or prove because it's a tautology. To really stress this point, Bertrand Russell, a famous philosopher, mathematician, and promoter of Einstein, theory of relativity, said, no, God created everything 2 seconds ago. Us, with exactly the way we are, with all our memories and all the atoms here in our bodies and in the rest of the universe, in the stars, galaxies, and everything else. So this is a formidable job for God to do. It's not easy to organize all these atoms and molecules. The task of modern cosmology is to make this task of the God easier. And we talk about that as the initial condition, to find out what was the initial condition and find as simple as possible models that could explain what we see, all the complexity, not only on the Earth, but all around us in the universe. So, as I said, the main task is to simplify this thing. Now, pre-1970 ideas were somewhat simple for the universe. Hubble had just 30 years before that had discovered the expansion of the universe. And we knew gravity, Newtonian gravity can decelerate particles, try to bring things together. And we ended up soon after discovery of the Hubble expansion and in 1963 discovery of a cosmic microwave background radiation, which tells us about the universe started with what we call Big Bang. There was really 4 initial conditions. One of them was how much ordinary matter and byproducts, if it is in the universe, which produces gravity, and how much radiation is in the universe. And Einstein had introduced a couple of new aspects of gravity, which was different than Newton's. The first one was that space, due to gravity, is curved, it's not flat. When Newton, before that, we thought the universe, the geometry of universe is Euclidean, or we call it flat universe. But Einstein said, no, we don't know that. It could be curved in different ways. And the other thing Einstein introduced was the cosmological constant. He called cosmological constant. Einstein had this theory of general relativity before Hubble had discovered the expansion of the universe. And when he applied his equation, he found out that it was not big. People thought the universe was static. He found out that the universe, according to his equations, that cannot be static. It has to be expanding or contracting. So he introduced this cosmological constant, a new kind of force, which opposite of the gravity, being instead of attractive, being repulsive, so it could balance each other and produce an expanding universe. Now, soon after that, maybe 10, 20 years after that, when Hubble discovered, Einstein thought this was the biggest mistake of his life and tried to tell everybody, forget about it, this is a mistake. But of course, once the cat out of the bag, nobody would pay attention to, even to Einstein. So this history of the cosmological constant evolved, and now we even call it dark energy, something different, and it could not be constant, it could be variable, and so on. So the pre-1970 cosmology tells us that there are really four possible universes that are all very simple. If you don't have cosmological constant, you get universes being decelerated by the gravity. So if the geometry is what we call closed universe, is positively curved universe, like a surface of a sphere in 2 dimensions, you get that red curve where the universe expands and then contracts, start from Big Bang and end up with what we call Big Crunch, where what will happen after that is not clear. And then it could be, if the geometry is flat, like Euclid tells us, it would be some sort of coasting, decelerating universe. If it's open, it will be accelerating eventually with the speed of light. But if you include cosmological, these are all decelerating universes, but if you include cosmological constant, after a while, cosmological constant repulsion takes over, and the universe starts expanding with acceleration. So this parameter h0 is what is known as the Hubble constant. Hubble measured that how fast the universe is expanding. And the inverse of that tells us something about the age of the universe. Now, when the cosmic ray macro background radiation was invented in 1963, was not invented, discovered by Penzias Wilson. Almost accidentally, they were to build the one on the left, the radio telescope on the left, and they were trying to look at interstellar medium, and they discovered this noise, couldn't get rid of it, and then eventually ended up discovering the Big Bang and won a Nobel Prize. About 20 years after that, a space telescope was built called COBE, which determined that the radiation coming from the Big Bang was, as expected, the intensity varied with frequency of radiation, as one would expect from what we call thermal or black body radiation. And they found out very accurately the second curve there, showing very accurately what is the temperature of the universe today at 2.7 degrees above freezing, above absolute zero. And then later on, bigger telescopes, space telescopes were built to find out what exactly how is this cosmic background radiation distributed in space. And one of the very surprising things they found out, it was extremely smooth. No matter which direction in the sky you look, you got exactly the same thing. But there was slight fluctuation in this temperature. The ratio of the variation of temperature to the mean temperature was something like 1 part in 10 to the minus 5. And this was a very important result, and so after WMAP Planck instrument, which was bigger and better, showed this fluctuation to high accuracy. Now, this observation, why is the universe so smooth, and also showed that the universe actually is the geometry of the universe also is very flat. That was a great puzzle, and that led to an idea called early inflation. Two scientists, Guth and Linde, did a theoretical calculation saying if you have dark energy, cosmological constant in form of a dark energy at the very beginning of the universe, like we are talking about the fraction of a microsecond, you could have universe also because of this cosmological constant expanding with acceleration and inflating, getting big, bringing everything into contact with each other and smoothing out the universe, and also flattening it, blowing it so much so the area of the universe we look like being flat. So, but the outcome of this is that now we need dark matter, which is 26% of the energy in the universe, and 69% of that is dark energy, and ordinary matter that we are familiar with was only 5%. And what we are made and the Earth is made is even much smaller. It's one part in that life is based on carbon, and Earth is silicon or iron, and so we are all very heavy elements. Only 1% of this 5% is what we have around us. So this is why we have no idea about why these quantities are the way they are, or what, in fact, what is the nature of dark energy and what is the dark matter. So that's why I think sort of the universe has become more and more strange to us. Now, dark matter was discovered by several observations. In the 1940s, Zwicky, the maverick astronomer at Caltech, studying clusters of galaxies, had found out that the clusters of galaxies don't seem to be in equilibrium. Equilibrium condition for things holding together by gravity is that the kinetic energy, how fast particles move around, that energy associated with that motion should be half of the gravitational energy of things being attracted together by gravity. So, but what he was finding that that wasn't satisfied, that kinetic energy is much higher than the potential energy that could hold it together. And if that was true, clusters should fall apart within 100 million years rather than 10 billion years. We knew the age of the universe is. So this he called missing mass. Now we call it the dark matter. So there's a lot of stuff there which is not being visible, is not producing radiation like stars that we see in the galaxies. The second observation came by several people, but led by Vera Rubin, and that was looking at the rotation of galaxies. A lot of galaxies in the universe are in form of a disk, and they're rotating disk, and the stars are rotating around the center. And she found out that when you plot the velocity of the objects versus the distance from the center, they rise initially and then stay flat. No matter how far you go, they're staying flat. And this didn't agree with the theory of gravity, because once you get outside what you see, the visible part of the galaxy, then from outside that, the velocity should drop because there's no more matter to keep them going fast. But they weren't dropping. This is shown by the curves in the 4 panels going down. So this said there is dark matter, and then most of the gravity of the galaxies is provided by the dark matter. And the panel on the right showed very detailed observation of the velocity versus distance of our own galaxy. There were some ideas that this could be caused by modified gravity and it's not dark matter, but as I'll come back, gravitational lensing showed that this actually is cannot be a modified verse of gravity, because when we look at clusters of galaxies which are colliding and merging together, clusters of galaxies have matter and they have gas, stars, and maybe dark matter and gas. Ordinary matter made of hot gas in this cluster of galaxy, as they merge, they get mixed up together, they interact. But dark matter is, the idea is that they are not interacting, so they go right through each other. And gravitational lensing found out the distribution of dark matter in this cluster of galaxies to be that 2 blue blobs which have come and gone through together, while the gas has gotten mixed up, and there's even the shock where they meet. So this proved that it was this missing mass has to be dark matter. It's not change of the gravity. Now, there are many attempts to find out what is the nature of this dark matter. This is a complicated figure, but there are many possibilities. A long time ago, we thought that the dark matter is made of what we call WIMP, which is weakly interacting massive particles which do not interact with ordinary matter and may not interact with each other either. So they only have mass, they only have gravity. And then later on, people discovered that standard model of elementary particle physics predicts being some sort of particle called axion, which is shown by the yellow band there, that these figures show on the horizontal axis, they showed you the velocity, the mass of the object, mass of this dark matter, and on the vertical axis shows how strongly they interact with each other. So we had a lot of laboratory experiments shown on the left, trying to start reducing, finding what is the limit of this interaction between the particle. And then they're getting, some of the part, they're getting close to the yellow, and they're eliminating that part. And there's a lot of astronomical observations shown on the right, which are very complicated, and they are also putting limits on it. So we still haven't been able to, so we're in this long possible range of masses for elementary particle for dark matter is what we have in nature. Dark energy was one way to, the cosmological constant, as it was interpreted as a dark energy, and it has very special kind of what we call equation of state. When we talk about gas or ordinary matter, we know they have pressure, they have energy density, and there's a relationship between them. And this was, dark matter is supposed to have what we call equation of state, where the pressure is proportional to energy with proportional constant W, which is about -1. And there's been lots of observation trying to find out this nature of the universe, the nature of this dark energy. And all those points are different ways of measuring this. And they all seem to be consistent with the W-1, which is Einstein cosmological constant. But there was also, people wondered if you have such a thing, could this W be variable in time, could have been different earlier than today? So there was, as if the time permits, there's more recently people claim that this is not the case, and as you go different times of universe, this number is not -1, but it's something different. As I said, if it's time, I may talk about that. So this is a picture that you commonly see. NASA made this famous picture that the universe began with a Big Bang on the left and expanded very quickly, inflated, showing by the bright region, and there was very hot gas, lots of radiation, lots of particles interacting with each other and stayed what we call thermal equilibrium, having the same temperature. Sometimes about 300,000 years old universe, this hot gas atoms and electrons combined, mainly hydrogen, electrons and protons combined and became neutral. Once they became neutral, then the radiation and the particles started not interacting, they decoupled from each other. And that green portion shows when this happened. And from then on, that early Big Bang radiation moved freely toward us, not interacting with matter anymore. And that's what those experiments showed us. And then for a while, the universe was very, in a way, there was only radiation, and matter was very cold, and no stars were formed. There were no stars, so there was no, it was what we call dark ages, and eventually stars, black holes, and galaxies were formed, and universe evolved, and nowadays is expanding with acceleration. So this is the picture we have now, but it's, as I said, if you expand the first 3 minutes of the universe, the yellow and the pink part, you can see that it has several phases, which most of it we don't understand. Somehow, dark energy causes the inflation, but then it undergoes a phase change, and the energy of dark energy turns into ordinary matter. You produce some of the particles we have when universe was 1 microsecond old. And when universe was something like 100 of a second year old, then nuclear fusion started, and particles fused together, and hydrogen was converted into helium. But then by the time 3 minutes came, that's all that happened in the universe. You couldn't build heavier elements. There was a time people thought in the Big Bang you could build all the elements that we see around, but it turns out not to be the case. Only we can produce some helium. And then we come with decoupling and the rest of the stuff that I talk. So it's a very complicated equation, situation now, with many unknowns. Okay, now I come to my main topic of gravitational lensing. Gravitational lensing, I'll say some historical notes first. The basis of gravitational lensing is the deflection of light by matter. We know when glass, for example, your light goes through glass, it gets deflected or so, and then you can rebuild from this concept telescope and magnify images of objects and see things. But Newton, after discovery of gravitational attraction and his equation of motion of particles, spent most of his time studying light. And he wrote a book in optics in 1704. And in that he mused that do not bodies act upon light and bend light rays. He wasn't sure whether this happened or not, but he wondered whether this should be the case. Now, 1820 with Solner, and later on Einstein, when it has a theory of special relativity, they took this idea and they find out, sure enough, the light ray should be bent. If a light ray goes by a mass at a distance r, given the mass of the object, you get a deflection by that equation given there. And this turned out to be incorrect, because when Einstein 10 years later produces 1915 general relativity, this number increased by a factor of 2. And then he calculated that the light ray grazing the sun, as shown on the left in the middle, will deflect by a very small amount of 1.76 arc second. Soon after that, 4 years after that, Eddington, a famous astrophysicist, of course you don't see this deflection when you can't see it during the daytime when you look at the sun. But during the eclipse, one starts beginning to the stars in the sky. So there was an eclipse in South Africa, and Eddington had an expedition going there, and sure enough measured that the stars which had seen the night before where they were when the eclipse happened, all the star position had moved, and he estimated by very close to this number that Einstein had predicted. And this, of course, really catapulted Einstein to stardom. Since then has been the case. Eddington also said that, as is shown on the lower part, the light rays could come from two ways, either one way, a bend, and then also the other way, so you should get two images. And then Charlson in 1924 said if you put one object behind a lens, a massive object directly behind it, then the light ray will come from all around, and instead of two images, you should see a ring. And this later Einstein calculated that the Einstein being more famous is nowadays called the Einstein ring. And that the image shows that how you have a small source in the middle of certain size, you produce a ring which is related to the size of the source. These are some equations telling you what is the size of this Einstein ring. And then it turns out you can get, when you are directly behind, the light rays is magnified by this maximum magnification given by this equation. And Einstein tried to see whether how much of this can be done looking at stars in our galaxy. So if I have a star and one star acting as a lens for another star, you are going to get an Einstein ring. It's easy to calculate. It's a 0.05 arc second. But you can get very high magnification. The star could be 200 times brighter. But the probability of this happened, Einstein correctly calculated, was 1 part in a million. So he says, of course, some of the small angle will defy the observation, and the probability for this happen is very small. So it's very unlikely that we ever see this. So this is the very calculation, but as we see, Einstein's prediction was wrong. Soon after that, Zwicky, who had discovered the missing mass or the dark matter in cluster of galaxies, said that, well, we don't have to think about stars acting as lens, but we can have galaxies. If you put one galaxy behind another one, the images will be fuzzier. It won't be as a nice Einstein ring, but still you could get Einstein rings of about 3 arc second, much larger. Even the telescope then, 180 years ago, could see that. And the maximum amplification now is very small. It's only 6. But the probability is very high. It's 1 in 100, because galaxies are much bigger relative to their separation than the stars are. The stars are tiny, essentially point-like light. So this could be possible. He also said that instead of galaxy, if you have clusters of galaxies, which he was studying, you put a galaxy behind it, then the magnification, the Einstein ring is larger, magnification is larger, and the probability is still the same. So he said, in principle, this estimate said that we can really see it, but he also correctly said, to make sure that this is the case, when we look at the image of a galaxy which is being lensed because it's far away, the spectrum should be redshifted more than the galaxies in the cluster, so that will be proof of this possibility. For some reason, after this very optimistic estimate of what we can do with gravitational lensing, that is possible to see, people completely forgot about it. But for no obvious reason, in 1963, 3 independent people, all different places, did exactly similar calculation, wrote papers very similar, telling about gravitational lensing, what could happen, and what sort of uses they will have. And so this sort of somehow revived the idea. And soon after, there were several PhDs and where we studied the effect of the gravitational lensing or astronomical observation. Because all astronomical sources, when we see the light from there comes to us, gets multiply bent by stuff in between, and this obscures their view. So now this we call them statistical lensing, but nowadays called weak lensing versus strong lensing, which produces Einstein rings. This now observational discovery came later. The first published observation of it was 1979, where Walsh, Carswell, and Wyman discovered two quasars very close together. It had exactly same spectrum. This bottom two shows the intensity variation they observed as a function of the wavelength, and you can see there are a lot of lines, emission lines, things going up, and they are identical on two of them. And this is very unlikely to be happening by accident. The small separation and this identical thing led them to say this is a cosmological thing. The idea of Eddington had that you get two images from a source behind a mass. And now, of course, we have studied this phenomena very much, and we see all sorts of images. Now, these are some images taken for, again, this quasars, which are very bright sources, going in behind the galaxy. And these galaxies, of course, are not simple spherical objects that cause the lensing. They are somewhat elliptical. And as a result, instead of getting an arc, which is rare, you get 4 images, which are nowadays called Einstein cross, 4 of them, and then one in the middle. Usually it's obscured by the lensed galaxy. So this is commonly observed. The second observation came, I was involved in. We published this 1986. We said this observation show that there are large arcs in clusters of galaxies, and they said the weight of evidence seems to favor the interpretation that these features are images of more distant objects produced by gravitational field of the cluster of the galaxies. We're seeing this arc. Our original 1976 thing is way on the left. You can't see it, but we saw some little arcs in there. And but later on, Roger Lenz, my collaborator, was building CCD instruments, which are essential for astronomical observation nowadays, and we got the better picture. And this, when we presented this at the AES meeting at Caltech, 1986, it created a lot of interest. LA Times wrote about it. And I made a mistake pointing to this nice arc, which is a part of Einstein thing. It looks like God created, God drew this nice arc in the sky. And as a result of that, I got a lot of mail from evangelicals saying, oh, how brave I am to talk about God, about the science. Or some of them were angry with me for even mentioning the God. So, and now, of course, space telescope like Hubble and the James Webb telescope, a bit bigger than the Hubble, seeing many arcs in there and much more accurately. And there are two kinds, as I said, that we are talking about now, two kinds of gravitational lensing. One which produces this this thing doesn't move. One that produces those nice arcs, we call it that strong lensing, but also you have things like that where galaxies seem to be elongated with a sort of concentrated way around the center, and we call weak lensing. Both these ways we can use by knowing the distances, by getting the spectra, knowing how far back the images are compared to the clusters of galaxies in front, we can measure how much mass is the universe. So this has become the bread and butter of astronomers and cosmologists to measure how much mass there is and how is it distributed and how this distribution has changed from beginning of the universe to today. So it's a lot of new telescopes are built to exactly study this aspect of gravitational lensing. For some reason, this is not moving. Stop moving up or down. There you go. Oh, okay. All right, now just some examples of use of gravitational lensing. Well, as I said, we use this for measuring mass. Most of the mass that we see, we call it visible mass, is made of ordinary stars, mainly hydrogen and then some heavy elements, helium and the heavy elements. But this is not enough for, as we know, we need dark matter. And the gravitational lensing, how it influences the motion of the other particles around each other and how it affects the light rays going by masses is one of the main methods we can measure dark matter, which doesn't emit radiation. Now, the thing that Einstein said is not impossible, eventually people try to measure. And this picture shows several experiments were set up to study what is the nature of this dark matter. There are two possibilities. One we call the WIMP, weakly interacting massive particles, and these people named the other possibility massive compact halo objects, weakly or weakly interacting. They gave it the acronym of MACHOs, just to be opposite of the WIMP. So they said if we have telescopes at the sun, the top thing shows the image of our galaxy, and we are someplace at the edge of close to the edge of the galaxy. If from there we look at the Magellanic Cloud, which is one of the satellite galaxies of our Milky Way, and instead of looking at one star, we can stare at 10 million stars at the same time. We can overcome this probability of 10 to the minus 6 that Einstein had calculated for one star lensing another. So what they expected that if you have something in the halo of our galaxy, like that dot where the red light goes through, it's a macho or whatever it is, star, dark star that we cannot see, then as a star, one of the stars in the Magellanic Clouds is moving around, they move past this. Instead of going straight through, then they go up. The two images are formed going up and one down, and then they get elongated, they become arc-shaped, and then their intensity will go up and down. And they discover several of them which they did that. The curves on the right shows how the intensity of the star changed with time. Of course, a lot of the stars are variable, so this could be it. But the fact that both red and blue lights varied exactly the same way, they knew this was gravitational lensing. But what the outcome of this experiment, which, as I said, was done about 30 years ago, was that the halo mass that we need for our galaxy is 2 times 10 to the 12 solar masses, which is based on the rotation curve. But the machos can account only for a small fraction of it. So the conclusion was most of it is there's some sort of WIMP or elementary particles that I mentioned. Now, I also mentioned the bullet clusters, these 2 clusters coming, and you can see a lot of galaxies around it. Some of them are the background, and they get images distorted, elongated, and based on this, we found out how the dark matter is distributed in here, and proved that it's dark matter. Now, this picture shows not only when we look at galaxies, the light ray coming from a galaxy far away, as it goes through, it gets bent many times. Then even the cosmic microwave background radiation, the Big Bang radiation coming 100,000 when the universe was 300,000 years old, that also gets distorted. And this distortion, study of this distortion by gravitational lensing allows us to really study that distribution of the cosmic microwave background to a high accuracy, and there's a hope that one day, once we understand this gravitational lensing, we can prove that indeed the inflation happened when the universe was extremely young. Okay, so this is a list of the things that gravitational lensing can do for us. First, the view of the first light affects the view of first light from the Big Bang, and also formation of first star hole, black holes, and galaxies. And also by magnifying the image of the distant galaxy, strong lensing means that we can really, it acts like a telescope. Now it makes objects stronger than we could have seen. And also, one important thing is that tells us how the large-scale structure of the universe was formed. So there are lots of new telescopes, especially one which we used to call Large Synoptic Space Spectroscopic Telescope, is now named after Vera Rubin, who discovered dark matter. And one of the tasks is this telescope will be to study dark matter, dark energy, and especially using gravitational lensing. And there are, of course, plans for even bigger telescope and many other space telescopes to do this too. So essentially, gravitational lensing has become. All right, I have 1 minute. Let me say something about the possible future. And of course, this future depends on all the unknowns I mentioned, the nature of dark matter and dark energy. If the dark matter is Einstein, the cosmological constant with this parameter W equal -1, then what we expect universe being accelerating. As it accelerates, galaxies get further apart. Eventually, they get out of our horizon, and universe cools off. So the universe will be a very dark and lonely place to live. About a year ago, almost a year ago, 10 months ago, there's a DESI project where they are trying to observe, well, they are using the 4-meter telescope at Kitt Peak with microfibers that each night they can take the spectrum of few thousand, 5 to 10,000 galaxies at the same time. This is very fast way of getting millions of galaxies. They're knowing their distances and their properties. And one of the things they have claimed to is that this W, which is supposed to be -1, is not -1, it's variable. It is now is -8, but is variable by that factor of 1 minus a, where a is the scale of the universe that I showed plotting the scale versus time. And as the scale of the universe changes, this dark energy, nature of dark energy changes. And recently there was a New York Times headline about, not this, but previous Science Times, saying that the astronomers are doubling down. They're claiming this to be correct, although there were some observations saying this may not be the case. It says astronomers get more than a hint that dark energy isn't what they thought. So, as I said, this is still controversial. Right when this came out, I was teaching a class on cosmology and assigned to my class to find out what would be the consequence of this new result. They didn't get it right. Some got it, some got close, but most of them didn't get it right. So at the last lecture, I did the calculation and showed it to them. And I won't go through the detail of this, but one consequence of this is that if you take those numbers at face value, the universe will not be dominated by dark energy as long as we thought it will be forever. It will stop dominated by dark energy, and dark energy will disappear. The red curve shows how the dark energy varies with time. 0 is present time, minus is negative past, and the plus is the future. And then in future, the universe will be governed by the amount of dark matter is in there, and also the curvature of universe. And we have some idea what the curvature of universe is today. And if you extrapolate that, when the universe is 1,000 times bigger than today, then the universe expansion is going to stop, and shown by these black curves, and then it's going to contract. So now you'll have oscillating universe going up and down. Whether they will bounce at the beginnings and have several oscillations or not, we still don't know. Anyway, this is preliminary result, and I still don't trust it enough to publish it, but maybe one of these days we'll have better data and we can do it. Anyway, so it's somehow, if this oscillating universe is possible, solves that unknown thing of how the universe began. There is no beginning, and there is no end. And one more thing I want to mention that is that when we look at there are some coincidences which are very interesting. Now, based on Hubble expansion of the universe, we estimate the universe is about 13 billion years old. That if we look at stars, we know the stars, like the sun, are converting hydrogen to helium. The sun now we estimate to be 4 billion years, and will continue converting hydrogen in helium in another 5 or 6 billion. So after 10 billion years, the sun will expand and maybe die out. And this may happen to all the stars. So there's another age we determined to be 10 billion years. Long time ago, geologists estimated the age of the Earth from the salinity of the ocean water, how long it took for all the rains to wash salt into the oceans and make them salty. And they came out a few billion years of age. And of course, Darwin tells us that the Earth has been around for more than that to produce all the living things in there. So these coincidences are confusing. why are these three different ways of measuring time in the universe so equal? One depends only on atomic physics, particles and molecules and how the atoms behave. Stars behave, it depends on nuclear physics. It's nuclear fusion which causes that. And of course, the Hubble expansion and based on age based on that is all gravity and Einstein theory of general relativity. And so somehow it looks like all these forces conspire together to create a universe that everything is similar. So long enough so we can produce stars and then produce life. So this has brought us back to what we call non-Copernican thing. Copernicus, when discovered that the Earth wasn't at the center of solar system, dethroned the Earth. And then we find that solar system is some typical thing in the galaxy. Our galaxy is very similar to that. So we thought Copernican principle is that we are not living in a special time or a special place. But now this coincidences has led us to believe, well, the main reason that we are here to study this complex universe is because all these forces of nature have conspired to produce a universe which gives rise to intelligent life to ask these questions. So this doesn't really solve the problem. This also creates more problem. Why is our universe so unique? This is called anthropic principle. So the whole universe is here for us to be run. So people created multi-universes, different universes which each can be having different laws, different ages, and so on. And this, of course, right now they're all connected. There's no way to detect them, but maybe one day some artificial intelligence will find a way to do that too, to find out how these different multiverses are connected. Anyway, sorry, gone a bit longer, and thank you very much.